thank you very much for the very kind invitation. Delighted to be here, and the bp-ICAM Annual Conference is a very important event for not just for BP, but for the University of Manchester and partners within the consortium. So I'm going to talk about metal organic framework materials. Before I do so, let me acknowledge an awful lot of people. Don't worry, I'm not going to talk about all their research, but I just wanted to highlight here how much work we do with national facilities, the neutron source at ICIS and at Oak Ridge in the United States, Diamond Light Source, ILL, the Advanced Light Source in Berkeley. Great credit goes to these people for all the structural and structural chemistry and analysis that they do for us, and also various collaborators around the world. Particular credit goes to my colleague Si-Hai Yang, who is part of the team and leads much of what I'm going to talk about. But clearly, without these people, I would frankly have nothing to say for the next 50 minutes or so. I realize many people here don't necessarily know what a metal organic framework material is, or necessarily even be interested in them. So my aim here is to try and show you why we work on these types of materials and why we think they're important. So you can construct three-dimensional frameworks illustrated here in a cartoon by combining metal centers with organic linkers. The organic linker can of course be varied. Likewise, you have the periodic table to choose from in terms of your metal center. But the resultant material is porous, potentially with a small pore or a large pore. There are all kinds of structural dynamic properties that these materials have in terms of flexing and breathing. You can introduce acidic groups, basic groups, metalloligans, open metal sites where there's vacant sites for catalysis. You can look at post-synthetic modification, so you can make your material and then modify it after synthesis. And there's various fundamental structural chemistry that is important here. If you regard these metal cluster centers or metal nodes as catalytic centers, then of course you have an array where your catalysis, your catalytic centers are evenly spaced throughout the three dimensions. And of course, you can then incorporate dopants, production of defect sites. So I'm going to talk about a variety of compounds, but mainly this Manchester Framework Material 300, which we prepared originally in Nottingham. So it's called also not 300, but like a football player, if you change your club, you change your strip, as it were. And we've been looking at a variety of metal 3+ complexes for hydrogen, methane, CO2, SO2, hydrocarbon binding and selectivity. And towards the end of the lecture, I will go into NO2, ammonia, and then show you some examples of catalysis, which I think is a very important area for the future. I emphasize the use of ligand as well as metal binding sites, and some of this work was reviewed a couple of years ago. So as an example, you take this hexa-carboxylic acid ligand, which of course you have to prepare, react this with copper-2 salt, and you end up with a polymer, because clearly each of those carboxylates will coordinate to a copper center, and you form a three-dimensional structure which incorporates this copper paddle wheel structure with 24 isophthalates. This is an isophthalate coordinated. The overall structure actually comprises of 3 cages, cage A, B, C. These are of different diameters, 10, 14, and 20 angstroms in diameter. And so you can view the metal organic framework as a series of fused cages, which I illustrate here. The material is prepared with solvent molecules inside these cages, inside the pores, which you then remove either via solvent exchange and heating, or solvent exchange and heating under vacuum. And this is an example of a gas isotherm for this material, MFM112. You can see here, this is at 0 pressure. Hydrogen is taken up to a total of 10 weight% at 76 bar. I emphasize that this is at 77 K. This is not at room temperature, but this gives a very nice high volumetric capacity. You can measure the isosteric heat of absorption. In this particular case, it's quite low because, of course, it's a physisorption process. And a very common feature of MOFs is that they have extremely high surface area. In this case, 3,800 square meters per gram. You can also analyze where the hydrogen, in this case deuterium, resides within the pores. So this is MFM 112. You can see the binding sites as determined by neutron powder diffraction. A1 is the first site, and it binds to the copper center, which has a vacant coordination site. The second site is the other copper, because these two coppers, this is a copper paddle wheel, these two copper centers are not equivalent because one resides inside the cage and the other one resides outside the cage. So these copper centers are different. I won't go through the details of the other binding sites. Suffice to say that this is very important for us to determine and design for future materials which absorb hydrogen better. You can take your ligand, you can extend it and elongate it in different ways. Of course, you can now design your pore cavity. And as you elongate the ligand, of course, the pore volume increases and the BET surface area also increases. And the net result is a range of isostructural materials, all of them porous with different pore diameters. You can tune these distances. You can look at, in this case, the argon uptake and then model this by non-local DFT calculations, and you get a plot of what the pore diameters and the pore width looks like. So this is 119, which is a particularly long elongated ligand. And as you can see, it's heading towards being mesoporous. The gas uptake for dinitrogen, for hydrogen, and for methane is shown here. This is all very nice, very high uptake, particularly for methane. This is a very high uptake for methane under these conditions. But I emphasize again, the problem with the hydrogen uptake is that the good uptake occurs, of course, at 77 K. And there is still a lot of work to be done in raising that temperature. So this is a real challenge for MOFs. In terms of hydrogen storage. We probably need to go to systems that have ligand binding sites as well as metal binding sites. And so this is again a series of MOFs. You've taken a phenyl group, replaced it by a nitrogen group, reintroduced the phenyl group, but put anthracene groups in here. And you form isostructural arrays of materials, but with different ligand centers, and look at the methane uptake as a function of ligand, as a function of pore size, and then determine the capacity between 80 and 5 bar, 35 and 5 bar, which is the deliverable capacity of any system, because you don't really want to go in a pressure swing system below around 5 bar, because then you need to actually go to a vacuum. This material is very interesting, the anthracene material, because the main binding site for CD4 is actually not the metal site, copper A or copper B. This is the paddle wheel you saw before, but actually it resides in this C3 symmetric pocket defined by the anthracenes. And by solid state carbon-13 NMR, we know that these groups, and by deuterium NMR, we know that these groups do not rotate. It's very fixed. So this is a very nice location for the methane to be stored. This is a very complex ligand. And one of the things I would say about MOFs is, of course, the ligand synthesis can be pretty expensive. But of course, in terms of scale up, once you have a ligand that you wish to scale up, the cost of this can be determined and reduced quite dramatically when you do the design of the synthesis. So this material with with copper 2 forms a very unusual structure. This is the nomenclature of these structures. There's a whole area of Moth chemistry defining this type of topological analysis. I won't go through this for obvious reasons. Suffice to say that this is a very porous material. 73% of its structure, once you remove the solvent within the pores, 73% of the structure has void volume. I just highlight here acetylene uptake. So this has a very high acetylene uptake. And the reason for this is shown in these neutron powder diffraction structures from ICIS. We can locate the acetylene binding sites. These are at the paddle wheel, copper paddle wheels, but also you will see that this particular pore fills preferentially to these other ones. We can nicely compare this with CO2. We have the CO2 binding sites there as well. So that gives us really very nice understanding how this host-guest chemistry works, what are the driving forces for good capacity, and indeed, what are the drivers for poor or low capacity. Here is the CO2 interacting with the paddle wheel. Importantly, and very commonly, we see supramolecular NH and CH interactions, and also interactions with the substrate itself. So the packing of the substrate is on occasion a real driving force for the substrate to go into the channels. Here are the binding sites for acetylene, and you can see an element of cooperativity. Once this site coordinates and this one binds, then this is a very nice site now for the fourth acetylene to come in to interact with number 1 and with number 2. Let me shift to carbon capture. This is a sort of schematic. Typically, carbon capture is conducted with amines. To this day, the very best materials, including MOFs, are amine-containing MOFs. But historically, CO2 capture was undertaken using this mixture of polyamines. There was a huge environmental penalty because these are corrosive, toxic liquids. And of course, in order to release the CO2, you have to basically heat the material up to release the CO2. So we were quite interested in looking at CO2 capture agents originally, but not using amine substrates. So this isophthalate, 4 carboxylate groups, react this with aluminium nitrate in the presence of PPZ, that's this. Under hydrothermal conditions, we can now make this material purely in water with an aluminium salt. We can make this material in multi-kilogram scale very cheaply. And we can make this Moth material MFM 300 aluminium. So the synthesis we can scale up as well. We can make multi-kilogram quantities of this Moth. It forms a very nice chain structure because the aluminium coordinates to the carboxylate, and other aluminium is here. So this is the chain, and the chains are bridged to give this very nice 3-dimensional cubic lattice. The pore sizes and various data are given here. This is not a particularly porous material, 1,800 square meters per gram. It is extremely stable. So this is the other feature of MOFs that people believe. They believe they're very expensive to prepare, cannot be scalable. In terms of expense, of course, some are expensive, but we can scale these up. And this material and other MOFs that I'm going to show you are extremely stable. Once you remove the water that is in these channels, you have 42% of this structure is just vacant and available for substrate binding. So you look at the gas isotherm, you introduce all these gases, nitrogen, CO, methane, hydrogen, argon, oxygen. They're basically all down here near the baseline. If you want to make a really, really poor hydrogen uptake MOF, this is the one. It has very low capacity. This is just to highlight methane. It has very low methane capacity, but you can put methane in here and it acts, this is a neutron structure, it acts as a rotor interacting with an OH group, which I'll show you in a moment. But you can see here, this is CO2 uptake, this is SO2, sulfur dioxide uptake, and it is reversible. You can see that this material is stable to SO2. Forgive me, I just froze. Okay, my screen froze there, forgive me. Okay, so what we have now done is combined single crystal X-ray diffraction, powder neutron, powder X-ray, inelastic neutron scattering, DFT calculations, and also synchrotron in situ infrared spectroscopy and also EPR spectroscopy linked to ENDOR to really analyze and give a comprehensive analysis using static and dynamic methods plus computational modeling to really understand what is going on with these MOF materials. Here is a powder X-ray diffraction structure. The inelastic neutron scattering and DFT fit this very, very nicely. I won't go through all the details for obvious reasons, but the basic structure is, here is your aluminium hydroxy species. Remember, if I just go back, this has an aluminium with two hydroxys. There's a hydroxy group on the aluminium, and it's this hydroxy that also bridges the aluminium centers. So therefore, that is hydrogen bonding to your linear CO2, but very importantly, there are 4 CH interactions to this terminally bound CO2. So there is 1 interaction to an aluminium hydroxide and 4 further ones to CH groups from the aromatic rings. You can see this T shape. The next CO2 comes in at perpendicular, links into that CO2, and then fits into this pocket really very nicely. So you can see there's really good complementarity between the substrate and the host pore, the substrate fitting very nicely into that pore. SO2 is very similar in the sense that, again, you have this OH interaction. There's the aluminium, very nice interaction, hydrogen bond there, and then 4 further CH interactions. SO2 actually forms a dimer. The oxygen from another SO2 comes in, interacts with the sulfur, and you can see very, very good packing. And this, of course, if you recall, I'll show you again, a very steep uptake of SO2. That shows it has a very high binding energy at around 60 to 70 kilojoules per mole. And that's why at low pressures, this material takes up SO2 very effectively. And it is also very stable. We can use IAS theory, ideal adsorbed solution theory. This was reported originally in 1965, and the Moth community have really taken to this as a method of analyzing adsorption isotherms using this approach. And I wanted to emphasize this. You can get analysis of SO2 CO2 selectivity, and you can see this is around 50. But remember, SO2 dinitrogen, you can see there's quite a lot of variation here. As you change the pressure, the selectivity changes. This area is actually not really very accurate, because when you have a substrate that is very strongly bound with a substrate that's very weakly bound, in this case dinitrogen and SO2 respectively, there are a lot of errors at this end of the plot. So really it's in this middle area that you get a greater accuracy in terms of your analysis of selectivity. But this material has very, very good selectivity for SO2. What happens if you take the vanadium-3 compound? Here is the hydroxy group interacting with the CO2. This material we can oxidize directly to a vanadium-4 species, and to counterbalance the charge, it's isostructural. These two are isostructural, but what happens is you lose the proton and the hydroxide is oxidized, or sorry, is reduced to oxy, to an oxy group here. It's not an oxidation, it's a deprotonation. So now you've lost the hydrogen bond capability to the CO2. So what happens in this material? Here is the CO2 interacting with the vanadium hydroxy, the 4 CH interactions onto the CO2. You now go to the vanadium, from vanadium 3 to vanadium 4. You have lost the OH group here. Here is the oxo group. What happens is that the CO2 twists, and it now interacts with the aromatic groups, which is quite exceptional. It's a weak interaction, and I would certainly not describe this as a CO2 capture agent, but at the same time, it does show very interesting fundamental chemistry here about CO2 interacting with polyaromatic groups. The industrial method for removing SO2 is essentially calcium carbonate going to calcium sulfate. Raw flue gas comes through, you have a precipitator, you have various fans and pumps, a reaction tank, and the clean flue gas goes through, in the sense that the sulfur dioxide is removed here as calcium sulfate. This begs the question, can you take this, remove the particulates, probably go through a cooling unit, and then use a metal organic framework to remove SO2? I'll show you this compound. This is again another copper material. It's very, very stable. This is very unusual for a copper 2 system to be so stable to SO2. The ligand we've used is tripodal again, but we've replaced this dicarboxylate group here with an pyridyl group. We form 2 compounds. One is MFM170, which has a coordinated water on a copper site. I'll show you that in a moment. You can heat under vacuum, and that removes this water and all the water inside these channels. Here is the copper paddle wheel. There is the nitrogen from this ligand coordinating to the copper. So that site is completely blocked. This copper has a water. This is this water, and you can remove that water by heating under vacuum. You've seen these types of cages before. This is how they pack. There are various very interesting structural perspectives here, which I won't go into. It has a good surface area, and as I say, is very stable. It absorbs SO2 very effectively. These are the isotherms at different temperatures, and it's fully reversible. And in terms of the literature comparison, this has the highest SO2 uptake of any known MOF. There's a whole range of them listed here. Some of these are actually not fully stable to SO2, and you can only cycle a few times. Here is the hydrated version of MFM170. It has a smaller pore size. It, of course, has a lower BET surface area because, of course, the water takes up space. And we can cycle this compound now 50 times. Here is the plot. The uptake of SO2 does not change. And with this material, here is the PXRD patterns. We can treat this in boiling water, pH 2, pH 12. On SO2 cycling, it does not show any deterioration by powder X-ray diffraction. The selectivity is good both for dinitrogen, and here is good selectivity against SO2. And we know where the binding sites are. This gives you a sense of the occupancy of the SO2 sites, not simply interacting with the open metal copper site, but also within the pores and interacting with the CH groups of the ligand. So let's go to the next step, and that, of course, is to try and do real separations. We can take various mixtures of gases. I just illustrate here helium, CO2, SO2, put it through a column of your MOF and look at what comes through. And this can either be a flow system, or it can be done by classical chromatography, where you just put an aliquot of gas through. And we can simulate whichever flue gases we wish to simulate. And using this method, you can see this is the breakthrough of SO2. This is dry SO2, and these are 2 cycles for wet SO2. The water drags the SO2, interacts with the SO2 and drags it through the column. And here is a breakthrough of a mixture. This is dry CO2 coming out, and this is dry SO2 coming out, and then this is wet, and this is wet SO2 and CO2 coming through. So you can see you can do wet gas streams, and of course looking at different concentrations. This particular one has 18% CO2 and 4,000 ppm of SO2. And here is a straight breakthrough experiment of SO2 and CO2 illustrated in a different way. CO2 comes through the column very quickly. SO2 is retained because it fits in the pores more effectively and then comes out later. So during this period, you're basically purifying the SO2 and what's coming out is pure CO2. You then introduce a flow of helium, and you can see the CO2 comes out very quickly, and then the SO2 is flushed out of the system. This leads us to other potential separations. So I'm very nervous to start talking about industrial carbon, hydrocarbon separations in front of experts from BP. So apologies if this is not state of the art in terms of a lecture, but just as an introduction, the separation of ethylene and acetylene is a very important industrial process. It has huge impact on Ziegler-Natta catalysis. So a low concentration of acetylene impurities tends to poison the olefin. This is our MFM 300 aluminium. We've done this with a whole range of different MOFs. This is acetylene uptake, ethylene uptake, ethane uptake, and methane uptake. So you can see at one bar there is good discrimination between those. We have all the structures of these materials. This is the acetylene structure, ethylene, ethane structure, all confirmed by single crystal powder X-ray diffraction or scattering or neutron diffraction, and also by DFT calculations. Acetylene is bound more tightly. That fits very nicely with the selectivity for acetylene via this OH interaction that I think is becoming quite familiar to you. And of course, there are a whole range of other interactions taking place, including acetylene-acetylene interactions. Ethylene is here. The distance is somewhat elongated compared with ethylene, and methane really doesn't interact here. It's sitting there because that's the only place it can go. It's sitting inside a pocket. And so you can look at the breakthrough plot. Here is the breakthrough of ethylene. Here is acetylene held and then comes out after about heading towards 2 hours or so. And a good way of looking at this as a host-guest system is, yes, you have a polymer, you have a three-dimensional framework, but it really operates in a supramolecular sense as a pocket in which you have all these receptor sites, CH interactions, OH interactions, pi-pi interactions particularly, and then dipole-dipole interactions gives you very high selectivity. And this is quite similar to biology, in which a whole number of relatively low energy interactions build together to form multiple site cooperative binding. Again, I'm slightly nervous to talk about this, again, in front of a BP audience, the separation of xylenes. This, again, is one of the most important industrial separations. It's described in this paper as one of the 7 world challenging separations. And the reason it's so challenging is because the boiling point, melting points, and all the physiochemical properties of these 3 isomers are very similar. And I should also add ethyl benzene to this separation as well. If you look at the shape of these MFM 300 systems, they vary quite subtly as you change the metal center, and this just illustrates the tightness with which xylenes pack inside this. The diameter of this pore fits xylene really very, very nicely. And in general, the tighter the pore, the more stable the system. Again, you can either do this via chromatographic measurements, where you pulse the substrate through the column, or you put a breakthrough system in which you have either 2 or 3 C8 components flowing through the column, and you collect the fractions and then analyze them. And just to summarize, you can see indium separates quite well, aluminium separates not at all. So clearly we are in the right regime in terms of size, property, structure, function to see differences between aluminium and indium, even though they're isostructural. So the pore diameter and size is very important here. The best separation we've seen thus far is by actually passing para-ortho and metaxylene first through a vanadium column and then put it through the indium column, and you get this type of separation. This of course is academic research. I'm not suggesting this has solved the problem, far from it, but at the same time it illustrates that MOFs do have a capacity and potential in this area. And we can look at literature comparisons in terms of the chromatographic separations. In this case, iron is particularly good for meta and para. Vanadium is pretty good. The indium is not so good. And there are some other MOFs that we see here. This is a particular MOF that's good for ortho and para. And that's one of the things I would emphasize. If you vary the MOF, you do vary the selectivity, and it's rather simplistic to say which is the best MOF. It depends on the conditions, the pressure range, the temperature, and precisely what it is you're trying to do. It's fairly obvious, I know, but at the same time, the discussions around these types of separations do get muddled, because it can be very difficult to define what is the best material for any particular separation. Here are some binary breakthrough curves. I again don't want to go through these in great detail, just to show you as you go from para-meta, meta-ortho, para-ortho, you get different separation capacities. And we can also do ternary breakthroughs with mixtures of orthometa and paraxylene, and also compare them with the pure components and make sure that it all is self-consistent. And again, you see the aluminium is really quite poor. The iron looks, at least under these conditions, to be one of the better ones, together with the vanadium system. Oh, sorry, this is the mixed indium vanadium system. So you can see that that is actually the best one. Again, comparing this with literature, different MOFs will have different selectivities. I just wanted to show this in general form. What we observe is often meta versus paraxylene selectivity in our systems. That seems to be something that we observe in many of these materials. And we link that into the structures of these xylenes. And I just illustrate that we can get structures. We can analyze the various pi-pi stacking interactions and then relate that back to the observed separations, or the lack of separation as it is. And you can see here ethyl benzene packs in a rather different way, and therefore does show a different type of selectivity. So we see both chromatographic and breakthrough separation of all 3 xylenes. We see that we can find the location of these xylenes within the host. We see strong affinity to metaxylene. I didn't go through that structurally, but metaxylene seems to interact very strongly with our MOFs. And what I've, of course, skated over completely is the whole issue of thermodynamic versus kinetic separations. Some of these xylenes actually enter the pores much more slowly than into other MOF materials. So there is a whole analysis here of thermodynamic and kinetic separations that complicates the issue, and actually needs to be very closely considered and understood. So now I move to something else, and I've worded it in this way because I set a question to the group, can a MOF be stable to NO2? And to be honest with you, I thought the answer would be no. Even though we had systems that are stable to SO2, I didn't really think that NO2 was likely. Here is the isotherm you've seen before. This is SO2, this is CO2 within MFM 300 aluminium. This is the NO2 uptake isotherm. In order to get this isotherm, we had to modify our equipment. If you imagine, all the seals, the tubing have to be NO2 resistant. This practically was extremely expensive and also very difficult to achieve, but we have achieved it. This plot shows stability over 5 cycles for NO2 in the aluminium MOF. This is a plot that we often, this is plotting the enthalpy. The enthalpy goes up as you load up NO2 and the entropy which goes down. So that shows, that indicates NO2-NO2 interactions as you load up. And this likewise suggests greater ordering as loading goes up. This is reflected in the structure, which I'll show in a moment, but this is the NO2 breakthrough, NO2 with CO2, NO2 with SO2. So you can separate these very noxious, highly reactive, highly corrosive materials within a very stable aluminium metal organic framework. There were complications with this structure. This hides a whole variety of sins. If you look at NO2 within this MOF, you have an NO2 to N2O4 dimerization, I think as many people know. So therefore, depending upon the temperature, you see different proportions of NO2 and N2O4. And I just illustrate this. Here is NO2 interacting with the OH group, and there's N2O4 within the pore. So this is a very complicated structure. It's temperature dependent because of the dimerization or dissociation of the NO2 within the pore. But we got there in the end with a static structure here with this stoichiometry. We can also analyze this by EPR and Endor spectroscopy. NO2 is a radical, it has a single electron. This is the EPR spectrum of NO2 within this aluminium MOF, which is diamagnetic, so there is no spin on the aluminium or on the framework. We link that to Endor. This is mixed EPR and NMR spectroscopy that analyzes the interactions between the nitrogen radical and the CH, the H protons on the phenyl groups, linked to DFT modeling with or without coupling to the OH and the CH groups. And purely from the EPR and Endor spectroscopy, we can simulate the structure which is shown here. And it is precisely the same structure as we see by neutron and powder X-ray diffraction, NO2 interacting with the OH group and the 4 CH groups. This tends to be a very strong motif here in terms of binding different substrates. Now we're going to move to a little bit more reactive chemistry. The vanadium-3, vanadium-4 couple, which I showed you before, you can oxidize vanadium-3 to vanadium-4 using NO2, which is then reduced to NO. So as you flow NO2 through a green or blue, greeny blue vanadium-3 column, you can see it goes brown because it's oxidizing to vanadium-4. After 120 minutes, the whole column has been oxidized from vanadium-3 to vanadium-4. And what's going on here is that the NO2 is being reduced to NO. And in the breakthrough experiment, there is the NO coming out. Here is water coming out. And eventually, as you get to this end, eventually the NO2 comes out. So this now begs the question, can we use this as a catalytic framework to reduce NO2 to NO, and obviously to dinitrogen and other nitrogen-containing compounds? This, I think, with my coordination professor of chemistry hat on, I think is the most remarkable structure. It is a zinc compound. It gives you MFM 520, 2,6-lutadine is a base, 2,6-dimethylpyridine. It's a very strong base, but it doesn't coordinate to zinc. So therefore, this does not get protonated under these conditions. You can form this MFM 520 material. I won't go through this analysis. Suffice to say that you can cycle NO2 with this zinc compound. I emphasize this is a zinc compound, and you can cycle it 125 times with NO2. It is entirely stable. You can do breakthroughs, PXRDs. Here are the isotherms. The structure of this with NO2, actually in this case, the pore is very tight and it fits N2O4 very, very well. So all the NO2 in the channels is in the presence, is actually in the form of N2O4. And so we can take this MOF, feed it an NO2 exhaust. The NO2 goes into the framework as N2O4, clean air comes out. The N2O4 can then be transferred into a flow of water and air. The oxygen in the air oxidizes this up to nitric acid. So NO2 goes in, nitric acid comes out, clean air comes out. Here is a summary of a recent paper we published on NO2 reduction to dinitrogen. So this shows dinitrogen selectivity using a doped aluminium MOF, doped with either copper, metal, or copper oxide, and it's showing very good NO2 conversion to dinitrogen selectivity. There's the NO selectivity and N2O selectivity. Under, I emphasize this, non-thermal plasma conditions. The turnover is very good under these conditions, and we're not using any ammonia or as you would, or urea as you would in other SCR catalysts. So again, I'm not saying that this is the best material you'll ever see doing this reaction, but I'm just emphasizing the potential of MOFs for this type of industrial application. Let me finish over the next 5 minutes or so to look at ammonia binding. Ammonia is a surrogate for dihydrogen, of course, and the MFM series is stable as long as it's aluminium or iron. You can see the indium breaks up quite quickly. This is the first uptake, and if you cycle, the ammonia uptake reduces on each cycle. Aluminium and iron are pretty stable. This is illustrated here for the aluminium compound at different temperatures. It's got very high uptake, 50 cycles with ammonia, very stable in terms of PXRD. And here is the structure. This was complicated because if you introduce ND3 into your MOF, there's a deuterium hydrogen exchange between the OH group here and the deuterium on the nitrogen. So this site is a mixture of H and D, and you end up with HD scattering or HD mixing on the nitrogen center. So exchange between those sites, and that complicates the structural analysis. But essentially, you see ammonia-ammonia interactions within that pore as well. So we've managed to not simply take a highly acidic NO2 or SO2, we've also done this with a highly basic corrosive ammonia system as well. It's very repeatable, very high volumetric uptakes. And of course, the next step is try to look at chemical reactions of ammonia, linking that into the release of dihydrogen, and of course, using this as a mobile store for ammonia, because the actual density of ammonia within these MOFs is extremely high. And we have one system now that is approaching the density of solid state ammonia within a pore at room temperature. Here is another piece of chemistry, which I think is quite exciting. You can take ammonia within the vanadium-3 system. The vanadium-3 goes to vanadium-4, and the ammonia goes to hydrazine. And you can follow this spectroscopically, you can follow this structurally, and see this chemical reaction taking place within the pore. Something completely different, just to finalize finish off the talk in terms of catalysis. You can make a defect UiO 66, which is a very, very stable zirconium material, first published out of the University of Oslo, hence UiO. It has a defect site. One of the bridging ligands here is missing, and you can selectively make defect MOFs, which is another area we're working in as well. And this is very powerful because it releases two hydroxy water groups. You have a vacant site, you can put a copper in there. And what we have done with this system is, again, reduce NO2 using this better selectivity than before. Again, I emphasize this is under non-thermal plasma activation. It's not done thermally at 300 or 400 degrees centigrade. Many of these MOFs, though, are stable up to 300 to 400 degrees centigrade, but catalysis at that temperature is a challenge for MOFs. But again, this is a proof of principle in terms of looking at NO2 reduction using MOFs. And I finish with some recent work. You can look at benzylic oxidations using this MFM 170 copper paddle wheel that was highly stable to SO2. This is the active site. It takes the peroxide, activates it. You go from copper 2, there's that water. Remember, this had a nitrogen to block off that site. It goes from copper 2 to copper 2, copper 1. It activates the hydroperoxide, and then you have a cycle here, illustrated here at the top. We can also construct carbon-carbon bonds photochemically. So you can photochemically activate the MOF. This activates your substrates. We can trap this and follow this by EPR spectroscopy. We can do the structural analysis of where the substrate is interacting with the MOF, how is it being activated, and we have various yields of various organic materials using this heterogeneous catalyst under these conditions. I emphasize under photoreductive conditions. And the final slide, apart from the next ones, is electroreduction of CO2. We've published a number of papers recently on CO2 reduction to formic acid. I emphasize this in terms of electrosynthesizing. This is bare copper mesh. There is the MOF on the mesh, and you can use this electrocatalytically. It's very effective for the reduction of CO2. The potential, of course, is too negative at the moment, but the MOF itself is stable under these conditions to generate CO2 reduction products. And finally, to emphasize the stability point, we have now had samples of NO2 loaded MOF and SO2 loaded MOF, NO2, SO2, and ammonia loaded MOF at Diamond for 3 years now, and the structure has not changed. The material is stable under those conditions for 3 years. So I would emphasize there are some MOFs that really are as stable as zeolites and really can do catalytic chemistry, substrate activation, substrate separations. Of course, not all of them are this stable, but we can do this. And we can make this aluminium MOF, as I say, in kilogram quantities to scale in very high purity. This, of course, is something else as a synthetic chemist I should emphasize. Some of these syntheses are not straightforward. You, of course, are forming insoluble products. Often they're carried out hydrothermally in a bomb. You heat the material, you heat the bomb up, the reaction for between a day and 2 or 3 days. You obtain a product, but it becomes very difficult to purify that product unless you break it up. So therefore, your synthesis has to be designed and be effective to get to a single component product. So I would emphasize that in terms of the synthesis, because I haven't really spoken very much about the synthesis other than to say that we can make these materials. So conclusions. We can make a range of highly stable MOFs with copper, zinc, zirconium, and other metals, energy and fuel substrates. We can look at find the location and define the locations using advanced spectroscopy, diffraction, and scattering. We have non-amine containing carbon capture systems, but at the moment, the most effective ones in the literature that I'm aware of are amine containing materials. We're using supramolecular interactions to OH and CH groups and the use of ligand sites to generate less environmental and energy penalties with an easy on, easy off mechanism. We're looking at the dynamics of carbon capture and also capture of other substrates. I emphasize the long-term stability and the use of MOFs for catalysis and photoactivation. And at a meeting that I chaired in the summer earlier this year at a Faraday discussion, there are now something like 20 to 30 spin-out companies around the world commercializing MOFs for very specific applications. And so we are now working on commercialization, as are many other groups and many other companies. And so these are exciting materials of the future. Various sponsors over many years, for which I'm very, very grateful. And I'm extremely grateful to my group. This is from a few years ago when we used to see one another by a Christmas tree. And we're going to have another picture like this, hopefully this December, with a Christmas tree behind us. Thanks very much indeed for your very, very kind attention.